Section 14.6, triple integrals. So let's begin with the definition of the triple integral. All right, so if f is continuous over a solid bounded region, which we will call Q, then the triple integral of f over q is defined as follows. The triple integral over q of f of x, y, z, dv, okay, so that's going to be equal to the limit as the norm goes to 0 of the sum from I equals 1 to n of f of x sub I, y sub I, z sub I, delta vi. Okay, all right, so now of course that is provided that this limit exists, and the volume of f of the solid region Q is given by volume of Q is given by the triple integral over Q dv. So just like what we saw with area, the double integral integrated over the area, here we just have the triple integral integrated over the volume. Now all of the properties of double integrals hold for triple integrals. There's nothing new coming our way here, so nothing crazy happening. Okay, we're just going to have to do another integral, so we're going to do them by iterated integrals. So let's talk about that. This is actually a theorem from our book. So evaluating the iterated integral for a triple integral. Okay, so of course we have f is continuous on the solid region Q. Okay, and if we have our boundaries on x, y, and now on z, we're going to set up our integral in the same way as we did with the double integral. Okay, so we have a less than or equal to x less than or equal to b. So x is going to be the last, right? We're setting this up for dz, dy, dx. So x is going to have the constant boundaries. Y can have boundaries that are functions of x. So h1 of x less than or equal to y less than or equal to h2 of x. And z can have boundaries in both x and y. So let's call that g of xy is less than or equal to z is less than or equal to g2 of xy. Okay, then we can set up our integral as follows. So I've run out of space. Let me move these down. So we have our integral from a to b of the integral from h1 of x to h2 of x of our integral from g1 of xy to g2 of xy of our function f of x, y, z, dz, dy, dx. Okay, so there we have it. There's our triple integral. Okay, so that's how we are writing our triple integral over Q of f of x, y, z dv. Okay, so the dz, dy, dx is dv, and then over Q we just have to set up our boundaries for x, y, and z. Okay, so let's do an example. So let's evaluate this integral. The integral from 0 to 2 of the integral from 0 to x of the integral from 0 to x plus y of, and here's our function, e to the x times y plus 2z, and we're going to integrate that first with respect to z, then with respect to y, then with respect to x. Okay, so just to make this a little bit easier to look at, I'm going to distribute the e to the x, so we can see each individual term. So that's e to the xy plus e to the x, 2 times e to the x times z, integrating with respect to z, then y, then x. Okay, so integrating with respect to z, the first term does not have a z, so that's a constant. Integrating a constant, we just multiply it by z. So this is our integral from 0 to 2, integral 0 to x. Okay, so we have e to the xy times z plus 2e to the x times z. We add 1 to the exponent on z and divide, so we get e to the x times z squared. We'll evaluate that from 0 to x plus y, and then integrate the result with respect to y and then with respect to x. All right, so these are z values. We are going to substitute those in for z. So this is our integral from 0 to 2, integral from 0 to x of, okay, e to the x y times x plus y plus e to the x times x plus y quantity squared minus, and plugging in a 0 into the first term we get 0, and the second term we get 0. Okay, dy dx. Simplify. So x plus y squared is x squared plus 2xy plus y squared, and I just distributed an e to the x to all of them. You do not have to distribute the e to the x. You can leave it out front until later. That would be perfectly fine. I just did it so that I could see each term separately without adding to any confusion about products. Okay, so now we're going to integrate this with respect to y. So this will become 1/2 e to the x y squared times x plus 1/3 e to the x y cubed plus e to the x x squared y plus e to the x x y squared plus 1/3 e to the x y cubed. And we'll evaluate that from 0 to x dx. Now you may notice that we do have some like terms, so I'll add those up after I do my substitution here. So notice that when we insert a 0 here for y, every single term contains a factor of y, so those are all going to go to 0. So we're going to just have the integral from 0 to 2 of 1/2 e to the x times x squared x plus 1/3 e to the x times x cubed plus e to the x x squared times x plus e to the x x times x squared plus 1/3 e to the x x cubed. Okay, so that's what we get when we substitute in the x, and as I said, substituting a 0, we get 0, so we'll integrate that with respect to x. So let's simplify this, make it a little easier to look at. So this is 1/2 e to the x x cubed plus 1/3 e to the x x cubed plus x cubed e to the x plus x cubed e to the x plus 1/3 e to the x x cubed. So every single one of these is an e to the x x cubed, so let's add up the coefficients here. So we have 1/2 plus 1/3, that's going to be, let's see here, get a common denominator, 3 plus 2 is 5, that's 5/6, plus 2, so that would be 12/6, so that's going to be 17/6, plus 2 more 6, that's going to give us 19/6. So it looks like I've got the integral from 0 to 2 of 19/6 e to the x x cubed, evaluated with respect to x. Okay, phew, all right, so now what? Well, we've got an e to the x and an x cubed, so that's typically going to be a good candidate for integration by parts, and we'll have to do it 3 times, so I'm going to integrate a tabular method. So let's do integration by parts, tabular method. Okay. So we've got plus, minus, plus, minus, plus, minus, etc. And then I'm going to need to start with my u's, so that's e to the x, e to the x, no, whenever you've got e to the x and powers of x, you want to let u equal your x term, and you want to let dv be e to the x dx, because that'll make the derivatives stay the same, or antiderivatives rather, our integrals will remain the same, but our derivatives will become simpler and simpler, which is what we're after. Okay, so u's are x cubed in this case, so that'll be 3x squared, 6x to the 1, then we'll have just 6 and then 0. Okay, now we'll do e to the x dx. Antiderivative is e to the x, e to the x, e to the x, e to the x. Perfect. All right, so with tabular method, you may recall this is your first term, second term, third term, fourth term. We stop at 0. So then what we end up with for our function here is that this is equal to positive x cubed e to the x, then minus 3x squared e to the x, then plus 6x e to the x, minus 6 e to the x. And all that is being evaluated from 0 to 2. Okay, so now notice this time plugging in 0 does not turn the entire thing to 0. The first, second, and third terms have x as a factor, but the third term does not, and e to the 0 is 1. So we can't just blow by and say, oh, 0 is going to give us 0. It's not. So let's go ahead and do our arithmetic here, our algebra. Plugging in a 2, I'm going to get 8e squared minus 3 times 4 is 12e squared plus 12e squared minus 6e squared. Okay, minus. Now we plug in the 0. So we're going to get 0 minus 0 plus 0 minus 6e to the 0 is 1. So that's just 6. So this is what we have. We have 8 minus 12 plus 12. Those cancel. Minus 6 is going to give us 2e squared. Minus negative is plus 6. Okay, ooh, you may have noticed I dropped something. Where did it go? Here, I dropped the 19/6, so I should have a 19/6 out front here. Okay, so this should be multiplied by 19/6. Shame on me for that. Okay, so we can simplify this a little bit. So we'll get 19 times 2 divided by 6 would be 19/3 e squared plus 19. And there we have it. Let me double check. Yes, there we have it. So that is our final answer, and that is correct. So good. If you have any questions about this one, please let me know. I feel like this section is relatively straightforward. There are applications, there are change of variables. It's the same kind of thing that we did in the previous section. So if those made sense to you, you should not have any difficulty with this. But as always, if you have any questions, please let me know.